episode 101, titled TLS Inspection, What It Reveals, What It Breaks, Performance Impact, we frame transport layer security inspection as a trade-off between visibility and privacy, because the exam expects you to recognize that inspection is not purely a technical decision. Transport layer security, often shortened to TLS after first mention, is designed to prevent on-path observers from reading content, so any attempt to regain visibility must be engineered carefully and governed explicitly. Inspection can improve security by exposing threats and policy violations that would otherwise be hidden inside encrypted sessions, but it can also introduce risk by concentrating sensitive data in inspection points and by breaking applications that rely on strict trust assumptions. The right answer in exam scenarios is usually the one that balances need-to-know visibility with minimal disruption, backed by clear placement and scope decisions. When you treat TLS inspection as an architectural and policy choice, you are aligned with how real organizations deploy it safely. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Inspection works by decrypting traffic, inspecting the content, and then re-encrypting it onward, which is effectively a controlled man-in-the-middle process performed by an authorized security control. The inspection device or service terminates the encrypted session from the client, presents a trusted certificate so the client will accept the connection, and then establishes a separate encrypted session to the destination. This split-session model allows the inspection point to see the plaintext content in the middle, apply rules or scanning, and then forward the traffic as a new encrypted stream. The critical requirement is that clients must trust the inspection point's certificate authority, and that trust must be managed carefully, or users will see warnings and may develop unsafe habits. The exam tends to test whether you understand that inspection changes the trust model, because the client is no longer talking directly to the destination in a single end-to-end cryptographic relationship. When you can describe the decrypt, inspect, and re-encrypt sequence clearly, you can reason about both the benefits and the side effects. What TLS inspection reveals is the content and context that encrypted channels normally hide, which enables controls that depend on understanding payloads rather than just destinations and volumes. Malware detection benefits because payload scanning can identify malicious downloads, exploit attempts, and suspicious scripts that would otherwise appear as opaque encrypted blobs. Data loss prevention benefits because content-aware policies can detect sensitive patterns, leaving the organization through web uploads, cloud storage interactions, and other allowed outbound paths. Policy violations become visible because inspection can see categories of content, disallowed file types, and prohibited commands that may be embedded in application protocols carried over encrypted connections. The exam often frames these as visibility-driven controls that reduce risk from web-based threats and data leakage, especially in environments where outbound traffic is dominated by encrypted hypertext transfer protocol secure. When you understand what inspection reveals, you can justify why an organization would accept its complexity and cost. TLS inspection can also break things. And knowing what breaks is important, because breakage often shows up as user-impacting outages that erode trust in security controls. Certificate pinning is a common breakpoint where an application expects a specific certificate or public key and rejects any substituted certificate, even if the substituted certificate is signed by a trusted enterprise authority. Some legacy clients break because they do not handle modern certificate chains or because they have limited trust store flexibility, causing failures that are hard to diagnose. Certain applications and protocols may also behave unpredictably when sessions are terminated and reestablished, especially when they rely on end-to-end properties or strict session continuity assumptions. The exam expects you to recognize that inspection is not universally compatible, and that exemptions and testing are part of any realistic deployment plan. When you anticipate breakage categories, you reduce the chance that inspection becomes a widespread availability incident. Placement decisions determine whether inspection provides coverage where it matters without adding excess latency or creating a choke point that harms performance. Inspection is most effective at converged egress points where high-risk outbound traffic passes, because concentrating inspection avoids deploying it everywhere and improves manageability. Placement should align with where the highest risk categories occur, such as user web browsing egress, endpoint update channels, and outbound data transfer paths, rather than indiscriminately intercepting every internal service-to-service flow. Latency matters because inspection introduces additional processing, and placing it in the wrong path can degrade critical applications and create user dissatisfaction that leads to pressure to disable controls. The exam tends to reward the idea that you place inspection where it balances risk and impact, often at controlled egress or ingress points rather than deep inside low-risk internal segments. When you can explain placement as a risk-based architecture decision, you demonstrate the kind of judgment the exam is looking for. Certificate handling is one of the most important operational aspects because TLS inspection depends on managing trust stores correctly, and mismanagement leads directly to warning fatigue and unsafe behavior. Trust stores must include the enterprise certificate authority that signs the inspection certificates, and distribution must be consistent across managed devices so users do not see errors. Warning fatigue is dangerous because users trained to click through certificate warnings may click through real warnings generated by attackers, which undermines the broader trust model. Certificate life cycles must also be maintained so inspection certificates do not expire unexpectedly, because expiration can cause widespread connectivity failures that look like a network outage. The exam often expects you to connect certificate handling to both security and reliability, because inspection changes the trust boundary and requires disciplined certificate management. When certificate handling is done well, users rarely notice the inspection layer, which is exactly the goal, because security should not train users to ignore critical warnings. Performance cost is a real consideration because decrypting and re-encrypting traffic consumes compute resources and adds overhead to connection establishment. CPU load increases because cryptographic operations are expensive compared to simple packet forwarding, especially at high throughput and with many concurrent sessions. Handshake overhead can also increase because the inspection point effectively participates in multiple handshakes, one with the client and one with the destination, which can add latency and amplify load when many new connections are created. The cost profile depends on traffic volume, cipher selection, session reuse behavior, and whether inspection includes deep content scanning that adds additional processing per byte. The exam tends to frame this as a capacity planning problem, where you must ensure inspection infrastructure can handle peak traffic without becoming the bottleneck. When you recognize that performance impact is predictable and measurable, you treat inspection as an engineered service rather than a switch flipped in a firewall. A scenario that justifies inspection is a regulated environment that requires outbound data controls, where the organization must demonstrate that sensitive data leaving through web channels is monitored and governed. In such a scenario, Outbound web traffic is mostly encrypted, and without inspection, content-based controls like data loss prevention cannot reliably detect sensitive patterns in uploads and form submissions. Inspection enables policy enforcement that can block or alert on protected data being sent to unauthorized destinations while still allowing legitimate business use where policy permits. The key is to apply inspection in a scoped way, focusing on outbound channels most likely to carry regulated data, such as file sharing, webmail, and cloud storage. Logging and reporting must be aligned to compliance expectations, but operationally, it still comes down to controlling risk without breaking productivity. The exam expects you to connect regulated needs to the visibility requirement and then to describe how scope and exemptions make the approach workable. A pitfall is decrypting everything and overwhelming infrastructure capacity, because all traffic inspection can create both cost explosions and widespread performance degradation. When you attempt to inspect every session for every user, the compute and throughput requirements rise quickly, and the inspection layer can become the primary bottleneck during peak usage. Overly broad inspection also increases the amount of sensitive content handled by the inspection system, which expands privacy and data handling risk and increases the complexity of governance. Operationally, it can also create a huge volume of alerts and logs, making it harder to separate meaningful signals from background noise. The exam tends to reward the idea that scope should be risk-based, because risk-based scope preserves capacity for the traffic that matters most and reduces unintended side effects. When you avoid decrypt everything thinking, you build a deployment that can be sustained rather than one that collapses under its own weight. Another pitfall is failing to exempt sensitive categories like health services, because inspection can create privacy, legal, and ethical concerns when applied to highly sensitive personal interactions. Some categories should be exempt for policy reasons, such as certain health-related services, financial services, or other regulated interactions depending on organizational policy and jurisdiction. Exemptions can also be required for technical reasons when applications use pinning or strict security models that will not function under inspection. The risk of mishandled exemptions is twofold. You either inspect traffic that should not be inspected, creating governance issues, or you fail to inspect traffic that should be controlled, creating a security gap. The exam expects you to recognize that exemptions are not a failure, they are part of correct design, and they must be documented and reviewed to avoid drift. When exemptions are handled intentionally, inspection remains both defensible and operationally stable. Quick wins often involve starting with high-risk categories and measuring impact, because phased deployment builds confidence and avoids unexpected outages. High-risk categories can include unknown file downloads, untrusted web browsing, cloud storage uploads, and webmail, because these are common pathways for both malware and data leakage. Measuring impact means tracking latency, error rates, handshake failures, and user complaints, as well as monitoring alert volume and false positive rates, so tuning can keep pace with coverage. This measured approach also supports stakeholder buy-in because you can show risk reduction alongside controlled operational impact, which helps prevent pressure to disable inspection when issues occur. The exam tends to favor this approach because it demonstrates mature change management and risk-based control selection. When you phase and measure, you treat inspection like any other critical infrastructure service that must meet performance and reliability expectations. A memory anchor that fits TLS inspection is decrypt, inspect, re-encrypt, exempt, monitor, because it captures the life cycle and the guardrails. Decrypt, inspect, and re-encrypt describe the technical mechanism, reminding you that inspection is a controlled termination and re-establishment of encrypted sessions. Exempt reminds you that not all traffic should be inspected, either for compatibility or for privacy and policy reasons, and that exemptions must be intentional and documented. Monitor reminds you to watch both security outcomes and operational health, including performance metrics and failure patterns, because inspection can introduce new failure modes. This anchor helps you answer exam questions quickly because it keeps the focus on scope, trust, and operational impact rather than on buzzwords. When you can apply this anchor, you can explain inspection as a system with safeguards rather than as a blanket capability. A useful exercise is choosing inspection scope from constraints, because exam questions often present competing priorities like compliance requirements, limited infrastructure capacity, and critical application performance needs. If the constraint is limited capacity, the scope should focus on the highest risk outbound categories and the most likely data egress paths rather than inspecting internal service traffic. If the constraint is strict privacy policy, the scope should include clear exemptions for sensitive categories and should ensure inspection logs and handling meet governance requirements. If the constraint is application compatibility, the scope should exclude pinned or fragile applications and focus on traffic where inspection is known to be stable, while alternative controls cover excluded areas. In each case, the goal is to select a scope that meets the primary risk objective while respecting operational and policy constraints, which is exactly the exam trade-off. Practicing this selection builds the ability to justify why certain traffic is inspected and why other traffic is not. Episode 101 concludes with the central trade-off. TLS Inspection restores visibility into encrypted traffic and enables controls like malware scanning and data loss prevention, but it changes the trust model, can break applications, and adds measurable performance overhead. Success depends on careful placement at meaningful choke points, disciplined certificate handling to avoid warning fatigue, and capacity planning to prevent inspection from becoming the bottleneck. Avoiding the pitfalls means not decrypting everything by default and not ignoring exemptions for sensitive categories and incompatible applications, because both errors can create operational and governance failures. The policy boundary rehearsal assignment is to take a realistic environment and narrate where inspection should occur, what categories should be included, what should be exempt, and what performance and failure signals you would monitor to confirm the deployment is healthy. When you can narrate that boundary clearly, you demonstrate exam-ready understanding of how inspection works and why its trade-offs matter. With that mindset, TLS Inspection becomes a controlled, defensible capability rather than an all-or-nothing switch. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.